Okay, guys, top of the hour. Lab this afternoon. Lab report, yeah, due when? Yeah, Wednesday. Hopefully you pretty much already got that done. We also have a quiz on Wednesday. And then next week we'll be finishing up the unknown lab. Okay, acid-base chemistry. Acid-base chemistry. Let's see how we did on back over here. How we doing this here? Get the show the complete Lewis structure of the ACL salt formed. We know the acid is HCl. What's the basic atom here? Nitrogen here. Okay. HCl, we need to always have bonds drawn out when we're doing mechanisms. Okay, these electrons are going to bond to the H, these electrons move on to the Cl. That's the basic mechanism. Basic and simple. Standard, fundamental. And then what's the outcome? The outcome is just boom, boom. I'm going to cut the molecule off. All that's the same. Now we have nitrogen with two methyl groups, right? And now the nitrogen bonded to what? The hydrogen. That's what this means. These electrons bond to the H. Okay. These electrons are being moved away from the H onto the chlorine. The chlorine has 3 long pairs. But now how many does it have? Now it has 4 long pairs, and it's no longer bonded to the H. Chlorine with 4 long pairs is a minus. Nitrogen with 4 bonds is a plus. There's your outcome. There's your salt, or ion pair. What's an ion pair? Pair ions. There you go. Ion pair, also known as what? A salt. Or ionic compound. Right? How do we do? Pretty straightforward. Including your mechanism. Mechanism needs to always be shown and used. It's the way to determine the outcomes. Hopefully you don't just want to memorize every outcome. You want to process for getting to the outcome, right? Your mechanism. Standard acid base. We just had to identify the basic atom. We know the acidic atom. The acidic atom is the H of HCl, not the H of any over here. Which is more acidic, HCl or HO? I mean, you know HCl is a strong acid. That's pretty much memorized, but hopefully you know why. Okay? How we do on that?
Is this the only mechanism that's favored for this?
Good question. What do you?
I was thinking because the methyls are kind of sterically hindered, and in my mind, I think that the lone pairs on the alcohol would attack the hydrogen, and making that a partial plus on the, and it would leave us water and leave a tertiary.
Which atom is most basic, the O or nitrogen?
The nitrogen is most basic.
Sterics doesn't hinder acid-base reactions. Acid-base reactions are also super fast because the H is a s orbital. Can we protonate these oxygens? We can. Once we start doing that, acid-base though is always faster than first. Down the road, we'll actually ignore acid-base. Because this is going on down the road too, but we just won't talk about it as much. There are other things that can happen. Okay. I think we're looking at making acid base. Okay. This is what I think, guys. I think many of you had questions about what we just did over there. What I would like to see is I'm over here, somebody goes, Dr. Stevens, I just don't get that. Can you please explain this here? Or why this? Why that? I would love it if I had said, okay guys, you all have 10 questions. Maybe stop by at this time, or how about after class, because we can't cover them all right now. So you got to get up here and get in here. You know? But I don't think everybody in this classroom just understood what we did as much as you should. And, all right? I won't go on and on about this because at some point we're going to go into second gear and we're going to keep going. All right? And we're going to get there real soon. Okay, which ones did we do? I think we did the top. We did succinimide. Did we do this one? No? How we do? We have succinimide. We have hydroxide. Outcome there. What's the base? Hydroxide. I think you learned Gen Chem. Hydroxide is a strong base. It's not that strong, but they call it strong in Gen Chem. It's moderately strong. There's a million bases that are stronger. There's your base. What's the acid? Must be this. What's the most acidic H over here? CH or NH? NH. Would you rather make an anion on carbon or nitrogen? Nitrogen. Nitrogen, more electronegative. Not only is it more electronegative, the anion is going to be resonance stabilized. There's your acidic H. Here's your base. How do you do your mechanism? These electrons what? Bond to the H. The base takes the H. And what do we do with these two electrons? Move them there. There was one there to begin with, right? Now how many is the nitrogen going to have? 2. And so we're going to have the nitrogen. Yeah? 2 lone pairs. You can see that? 2 lone pairs. Charge of the nitrogen now? Negative. And what did we make? Yeah, we made water here. There you go. The strongest base reacted with the strongest acid. And which side's favored? The acid over here has a pK of 8. What's the acid over here? The H. Which thing has the H? There's the H there. Where's the H at now? It's here. This thing's the acid over here. It's pKa. 16. Which side's favored? 8 or 16? 16. 16. The weaker acid is favored. That side's favored. So the equilibrium is really like this. That side's favored. By how much? 10 to the 8, which is what? 10 to the 9 is a billion. 10 to the 8 must be 100 million. At equilibrium, you got 100 million of these anions here. This is the main organic compound. 100 million and only 1 in that form. Question, is hydroxide strong enough to deprotonate succinimide?
Yes, that's what we just did.
Exactly, that's what we just did. We deprotonated it. We removed the proton. Acid-base reactions, protons, proton transfer, remove the proton. Simple question, is hydroxide strong enough to do that? Yes. Because it just did it. 100 million to 1. Yeah? That's the type of question you ask, how strong a base do I need? I can show you some bases up here where this side would be favored. That is, nothing has happened over here. It has not been deprotonated. But hydroxide is strong enough to do this. It'll do this completely. I mean, I consider 1 to 10 to the 8 pretty much complete. Right? If there were 100 million students in this room and I wanted to get you all out the door, and all but 1 was out the door of the 100 million, would you say my job is pretty much complete? Or I mean, 99.99999% complete. I mean, by the way, no equilibrium is ever 100% complete. In theory. In practice it is. In practice this is complete. Question?
If we're asked a question like that on the test, is hydroxide strong enough to deprotonate succinimide?
Will we have enough time to write out the mechanism and the whole reaction, or is that something we just need to know fast for a multiple choice question?
Well, you're not going to know it unless you go through the thought process.
Okay, so it'll be a question that would allot us enough time to actually
Well, I'm
do
not
the
going to
work.
guarantee that. It depends on how much time. You need to be able to think quickly. It needs to become second nature. Hopefully there's a lot of Gen Chem here, and we're just sort of building upon that. You got pKa's, 8 versus 16, which side's favored? Bam, you know. Next one. Which one's the base? What's the most basic atom on the board here? These are nitro groups. Nitro groups, that's a functional group. It's not on our list. You'll see it in organic 2. The nitro group is N, double bond O, single bond O. The nitrogen is positive and the oxygen is negative. Coming off there. There's no way to draw this functional group without it being doubly charged, but it's net neutral. Okay? It's your nitro group. This is an anion, but it's not basic. Nitro groups there's no acid base to nitro group. I'll just tell you that. It looks like this could be basic, but it's not, because these electrons are heavily pulled towards this positive nitrogen. And this resonance. I mean, this is conjugated. One of these lone pairs is in the p orbital because of the p orbital here. It's a good structural consideration, but nitro, no. So what's the most basic? Tertiary amine, sp3 nitrogen. We said sp3 nitrogen, neutral. Even though it's neutral, it's a good base. And I showed you a page of natural products that contain such basic nitrogen called natural products that contain basic nitrogens are called what? That's right, alkaloids. Basic nitrogen. Where's the most acidic H? Yeah, all you got here is OH and CH. Okay, we need to draw in the bonds if we're going to do mechanism. You got to have bonds. Can't work with condensed structures. Just draw the bond in. These electrons take the H. These move behind. There's your product. This is called triethylamine because it's 3 ethyls. Triethylamine. Now bind into an H, right? Positive charge. And what is the other species going to look like? Oxygen with what on the oxygen?
3 lone pairs.
3 lone pairs. And charge? Yes. There you go. It all comes from the arrow movement there. We moved another lone pair. There's 2 original, right? 2 original. Where'd the third one come from? Right there. These electrons move over here as a third lone pair. There's your salt, your ion pair, as a result of this acid-base reaction. Which side's favored? What's the acid over here? Which molecule contained the H? That one, pKm1. What's the acid over here? Which molecule contains the H? That one. What's its pKa? pK is 10. I told you right here. I listed under here. This is a base. Why am I given a pKa? We don't use pKb's in organic chemistry. Instead, we give pKa's. But if the pKa is referring to a base, well, hold on. If the pKa is given for a base, it's actually referring to the conjugate acid. Whenever you have a pKa of a base, the pKa is referring to the conjugate acid. What is the conjugate acid? This. The pKa I gave refers to this. It's 10. As long as the molecule is acting as a base. Okay, which side's favored? 1 or 10? 10. So that side's favored by how much? 10 to the 9? A billion? So at equilibrium, you got a billion of those, a billion of the oxygen anions, and only one in the neutral OH form. Is triethylamine strong enough to deprotonate this guy?
Yes.
I'd say yes. What type of functional group is this if you ignore the nitro groups? Name of it. Phenol, or phenol, however you want to say it. I say phenol. It's a phenol. It's actually a trinitrophenol. It's actually 2,4,6-trinitrophenol. The nitro groups make that much more acidic. Most phenols have a pK of about 10. Nitro groups are very electron withdrawing because this nitrogen is pulling, makes it much more acidic. Actually, that's called picric acid. It's so acidic it's called an acid. But it's not a carboxylic acid. It's a phenol acid. It's actually also explosive. Next one. By the way, this would be called the picric acid salt of triethylamine. Make sense? Back over here, when we drew this, started over here. This salt was called what? Back over here, when first thing we did? That's tramadol. We drew the hydrochloride salt of tramadol. That was our product. It was the hydrochloride salt. Or I would just say the HCl salt of tramadol. Because it reacted with HCl to make the HCl salt. That's just terminology. Next one. See, this is phenol without the nitro groups, pK of 10. This is called pyridine. I've already commented on this. I did that up there. Outcome here. Most acidic H. All these are CHs, CHs, OH here. Where do you want to make anion in? Right here, right? Where's the most basic atom? H here. These electrons make bond to H. These move here. What do we have? Now bonding to H, that's a positive charge. And we have the there you go. There's your ion here. You get it right? Question?
Aren't those lone pairs involved in the P orbital, correct? Because they're adjacent to the double bond?
No, here?
Yes, sir.
No, that lone pair is in a sp2.
Okay, but wouldn't it would be basic then?
sp2?
No, I'm incorrect, I'm sorry.
sp2 is not as basic as sp3, but sp2 still has some basicity. I mean, pK is about 5, but that's for a base, and once you start understanding that. Where an sp3 nitrogen has a pK more like 10. There. You need to really think about what these numbers mean. And lower pK means the acid is stronger. That means this is a stronger acid than what we drew up there. That means this wants to give up the H more than what we drew up there. It wants to go back. Well, if it wants to go back, that means this doesn't want to go forward. And if this doesn't want to go forward, that means it's a weaker base than the other. Okay, let's look at that. That sometimes comes up. I'll draw this more clearly. What's the hybridization of this nitrogen here? And what type of orbital is that lone pair in? It's sp2, and the lone pair is in what type of orbital? It's sp2. I see sigma bond to carbon, and pi bond to carbon, right? And the lone pair has to be in sp2. What's the question about that? Why were you thinking something else for this lone pair?
Oh, I was thinking incorrect. I was thinking that it wouldn't readily give up those electrons wouldn't readily attack an H when they're in the sp2 orbital.
If they were in sp2?
Yes.
No, sp2 can be basic. I thought you were thinking this was p orbital.
No, sir.
Okay, lone pair is not in a p orbital.
Yes, that's what I was trying to say.
Anybody think that lone pair is in a p orbital? I anticipate that many of you might think that. Anybody think that? Why do you think that? Well, just because a double bond is near doesn't really mean much. That's too generic and vague. What do you mean by near? Well, still, that's not real. That's way too vague. You need to talk about p orbitals. And once you start talking about p orbitals, then you have to make sure that they overlap. So you just can't say double bonds nearby. That really doesn't tell you anything, other than lead to possible confusion. And okay, you got to narrow down. Now we did say anytime a lone pair is next to a p orbital, is going to want to be in a p orbital. There are p orbitals over here. But this is a case where, no, it can't be in a p orbital. You already have 3 p orbitals here. If we draw the orbitals, okay, I see pi bond here. Pi bond comes from 1 electron, 1 electron. Overlap to make pi bond. And I've got that shown here. Well, this one's actually interacting over here, 1-1 pi bond. See that? Yes, there is some interaction here, which we can't see from this incorrect structure. This p orbital is also interacting over here. That's called conjugation. We just have to know it's there. The lone pair is here. It's in the trigonal planar. And the way I've got it, those are going back, and the lone pair is coming out. That's the trigonal planar. Yes, there's p orbital next door, but it's already interacting with the p orbital that's here. If I put this in a p orbital, what am I going to do? Break the pi bond? No, you're not going to do that. This is in a hybrid. Now, if there was a second p orbital over here, then we could say there's a p orbital next door that this could interact with. Basically, when I say there's a p orbital next door, what I'm not continuing to say is it's got to be able to interact with the p orbital next door. Okay? Typically, the only time you're going to see this exception is when it looks like it's sp3, but it ends up being sp2. When it's sp2, it's rarely going to go to sp. No, it just can't. Here's another reason. sp, what geometry is sp? Linear. Can this CNC be linear? Think about it, it can't. It's in a ring. It has to be. If it went linear, it can't. It's in a ring. So that's another reason it's not going to do it. It's just plain old sp2. There's really no exception here at all. You got double bond, single bond, lone pairs, and sp2. Okay? sp2 nitrogen can be slightly basic. It's acting as a base here. If it ain't that nitrogen, what is it? If it ain't that nitrogen, there is no base. It has to be that. But here's the question we can ask, though, is, first off, which side's favored? That's the acid over here, 10. What's the acid over here? Which one has the H? There it is. Okay? What's its pKa? 5. Because the pKa of a base refers to the conjugate acid. Which side's favored, 5 or 10? 10. This side's favored. Question, is pyridine strong enough to deprotonate phenolic? By strong, I mean, is it going to take it to that side substantially?
No.
No, it does not. It barely goes to that side. This side, it stays here. At equilibrium, what's the ratio? Difference of 5. That's 10 to the 5. So at equilibrium, we have 10 to the 5 of this side and only 1 of that side. So that means, basically, out of every 100,000, only 1 is like that. Out of every 100,000 of these phenols, only 1 has been deprotonated. Sounds like pyridine's doing a lousy job. Pyridine's not strong enough to do this. But that doesn't mean we still can't show an acid-base reaction that would be most likely to occur. Unless you think there's some other acid-base reaction we should have shown here. Should we have shown the nitrogen taking a CH? No. The OH is most acidic. Okay. How about the last one? This is an amino acid, an alpha amino acid, because carbonyls, first carbon away is often alpha, the next one's beta, etc. Here the amino group is on the alpha carbon, alpha amino acid. It's carboxylic acid. Of course, these are the building blocks of the proteins. You'll learn these in biology and biochemistry. It's just one molecule. That doesn't matter. This could have been one molecule. I mean, these could have been bonded together like that. We still could have did the same reaction up there. It's just our products would have been bonded together. Right? Don't draw this in, but it would have been the same thing. All right? Just because it's one molecule doesn't make a difference. What's the most basic atom in the molecule? sp3 nitrogen. Okay, what's the most acidic H in the molecule? The H of the carboxylic acid. All right, this takes that. Now, here's where we're a little bit different. It could be internal. This could rotate up. By the way, we're going to start doing rotations. All right. But we can also be just two different molecules. Okay? I can draw just another molecule. And with amino acids, it's this R group here that varies. This is all constant with the amino acid. I could draw another molecule and then have this nitrogen take the acidic H of another. And that's going to, if I just showed the top one, this is now what up here? NH3, I'll draw them all out, plus. This could have been shown condensed, NH3 with a plus all condensed. Here's R. But how's this over here going to exist? Let's focus down over here. Come like this, yeah? Because while this nitrogen is taking the H of that one, guess what? The nitrogen of some other molecule is taking that H. It's all happening. So I just drew one molecule over there. There's your outcome. We made an ion pair. It's just they're in the same molecule. Which side's favored? The acid over here is 5. What's the acid over here? This guy is 10. Which side's favored? 10 is favored by how much? 10 to the 5. 100,000? So at equilibrium, it's 100,000 to 1. So let me ask you, this is just one compound. How does it most likely exist? Everything neutral or in that form? That form, we just said that. 100,000 to 1, it exists like that. Amino acids are doubly charged. But it also depends on what pH you're at. At very neutral pH, they're like this. But this can vary once you bring pH into it. Anybody know what you call a molecule that has, it's net neutral, but it's two different charges? Starts with a Z. Uh-huh.
Zwitter ion.
The Zwitter ion, yes. That's how an amino acid exists. You expect this to be soluble in water? How soluble in water is this? I would say it's very soluble. Because when I look at that structure, I know that it really exists like this. It's just ionic. It's very soluble in water. But again, this can vary depending on pH. That's a different discussion. We've done that already. We were doing that at the end of class last time. I don't think we did an example here. Acetic acid, how will it exist at pH of 7, which is blood pH? You got to know the two forms. You got to know the acidic form, the basic form. Okay? An acid. When an acid acts as an acid, it becomes the conjugate base. We should be able to show the conjugate base. Here's the acid, here's the conjugate base. Which one's going to be favored at pH of 7? We know pH. We want to determine B versus A. To do that, we got to know pKa. What is the pKa of this? 5. You can plug in your math. So 7 equals 5 plus 2. For log of B over A to equal 2, which is a positive number, which one has to be higher, B or A? B, correct? That's using the math, or you can do the take-home summary. Here's the take-home summary again. Let's look at this. You've got one variable here and one constant. pK of 5 is a constant. It's never going to change for acetic acid. This is a variable. We can change that to anything we want. Okay? Here's the way I approach this. The thing that can change, is it sitting on the high side or the low side of the constant? Is 7 on the high side or low side of 5? High side. It's greater than 5. That's the high side. Okay. Is the high side, is that the basic side or the acidic side? Higher the number is more basic. The high side is the basic side. Okay. 7 is on the high side, or thus basic side of 5, and so the basic species is going to predominate. That's the same answer we got by looking at the math. But it was a more rationalized approach. Okay? B will predominate. By how much will it predominate? Well, this is, again, is the difference in your two numbers, log numbers. 5 and 7, the difference is 2. 10 to the 2 is what? 100? So at pH of 7, it's going to be 100 to 1. Okay, or I'll do this, 1 to 100. There's your ratio. The B form predominates, the acetate ion. That form predominates at pH 7. Very often, students will say, okay, 5 is on the low side of 7, so it's acidic. No. You want to look at where the variable number is. Where the constant is here. There's your mark. Variable, where is it sitting at? Is it high or low? It can move. Because I could say, what about if I said pH of 2? Right now we're at 7, above the constant. 2 would put us down here. And that's the which side? That's the acidic side, low side. Okay? But all the time I see students going the other way and saying, hey, 5 is below 7. Okay? Don't do that. Just some miscellaneous comments down here. You should know that already. You know the typically conjugate acid-base pairs. One typically neutral, other one's charged. Doesn't have to be that way. I reckon you could go from a minus to 2 minus, or something like that. But in organic chemistry, usually we don't see many 2 minuses or 2 pluses. Organic chemistry, any acid base is usually going to be a neutral and an ion, as opposed to an ion and a double ion. So for me, a conjugate acid-base pair is usually a charge and a neutral. A charge and a neutral. What else is here? The idea of making salts, very important. Codeine, uncharged form. React with ACl, make the ACl salt. Protonated, ion pair. Large number of drugs are given as salts. Why? Because they're ionic now, they have ionic nature. Of course, this drug has lots of covalent nature as well. But it does now have some ionic nature, and that increases the water solubility. Equilibrium. This reacting with HCl. Is this going to be the favored product? Or is it going to stay like this? ACl has a pKa of -5 or some very low number. This has a pKa of about 10. Does it say that? 8.2. 10 is very sort of generic. Which is favored, -5 or 8? 8, right? So this is favored by how much? 10 to the, what is that, 100 gazillion? At equilibrium, you got 100 gazillion of these and only one of those. Yeah. A strong acid is going to completely convert it to the salt.
I was about to say, so usually a acid-base reaction with HCl, you can assume most of the time that
It's
the other
pretty
side will be
complete.
favored.
Right.
'Cause it'll complete it.
But instead of just assuming, I'm trying to explain the numbers and let you see how the numbers tell us the same answer. Okay. There's other things here. On the back, acid base. A lot of review. We mentioned most everything back there. Hopefully that's a good review. No extra charge for that page, okay? All right? That's a gift from me to you. Any questions about acid base at this point? Okay, please keep working with it. Next handout is one you printed on your own, alkanes, cycloalkanes, including nomenclature. We'll come back to nomenclature. I'm going to jump ahead a little bit because I want to introduce the topic before our mini break on Monday. We won't be back until Wednesday. We'll turn in your lab report here in class on Wednesday. Everybody? Oh, and by the way, I want to pass back the other group's quiz. Let's do that at the very end as you leave, so when you pick it up, you can just leave. Please remind me, I gave the other Thursday group theirs yesterday. Friday group, I want to give you the quiz today. We do have a handout, though. We'll cut it in half. Just one handout. Purple. Okay, while that's going around, let me introduce this a little bit. We're going to move into alkanes and cycloalkanes, hydrocarbons. And this will finish up material for test 1. Test 2, we'll move into alkenes. Okay, alkene. And also alkynes. So we're starting to look at functional groups in more detail here. All right. With alkanes, we have the nomenclature. You're working on that. We'll go over that page, or we'll finish that up. There's one I did not do on the video, etc. There's a few miscellaneous things in the beginning of the handout. Two of the major things in this handout is conformations. Conformation is basically, here's an alkane with 2 green substituents. Because of sigma bonds, it can rotate. All right, we've said that before. Well, we need to understand what's the possibilities of the rotation. For example, when this compound is hanging out on a Saturday afternoon, watching the Georgia game, are the 2 green groups going to want to be opposite to each other like that, or like this? Well, that's 2 different conformations. What's a conformation? It's just how the molecule is oriented as a result of being able to rotate. You can have that conformation, or maybe that conformation. Or we can have that one, or that one, or that one. There's 1,000,001 conformations. I can just move it, and that's a different conformation, just like here. Boom, that's a different conformation of me. Here. Okay? And then I can ask, when I'm just standing around, do I stand around like this, or do I stand around like this? Why? We're comfortable. It's lower in energy. Same thing here. We're going to say, what's higher in energy? Would it rather be like this or this? Okay? These are all conformations. Everybody got the sheet? Purple. Conformations up top, sometimes called conformers, or even sometimes called rotamers. Okay? The other thing we need to be able to do is draw these on the board. How do we draw these? Okay? I want to get into this kind of quickly so we can introduce it before the break. Otherwise, we will lead into it a little bit more. I'm going to go through on this purple sheet here. We draw these on the board as Newman projections. All right? Different, Roman numeral 1A, different way to show conformations. Let's actually go over here in the handout, what that you printed. Look at ethane here. Okay, ethane. You might show it like this, but that doesn't have any of the bonds to show the tetrahedral nature. This is showing the tetrahedral nature of each carbon, 2 in the plane, 1 forward, 1 back. Yeah. This would be called a perspective drawing, because we're able to see the perspective of the bond, how it's oriented. Okay. It's really called perspective drawing. Sometimes you may see a sulfur structure. I'm not going to do any of these, but sometimes they come up. You have to view this as if the 3 are down in the front, and that's going kind of back up there like that. That's drawn flat, ugly bond angle. We have to know in real life that these are really coming forward, etc. That is one way to do it. And it's worth looking at that a little closer. We're going to be working more with these. How do you draw this on the board? And in a Newman. First off, let me change these greens to just black. Then we will have just ethane. What we have here is 2 carbons here. These 2 carbons. And in each carbon, I'm saying that these are H's. Carbon with 3 H's, carbon with 3 H's. All right? Just like this. And we can have it on the board. This carbon, 1H straight up, okay, as if the board is like this. And then 1H is forward, and the other H is back. Over here. That H over there that's going in the plane is straight down. Okay? Straight down in the board, as if the board was here. And thus this H is coming towards you. So if the board's here, I got 2 H's coming towards you, 2 H's in the plane, and then 2 H's going back. But this one is coming a little bit down towards us, where that one's coming a little bit up towards us. Bold is coming towards us, dashed is going back. There it is on the board. Another way to draw this is, instead of drawing it as if you're looking from your view, like that, is to draw it like this, that view. What do you see there? Can we draw that on the board? Looking down the 2 carbons, carbon 1 in front, carbon 2 in back. How do you draw that on the board? That's done with a Newman projection, also called circle, circle, dot, dot. All right? Remember that? Circle. Dot in the middle. We want to draw this on the board right here. The dot in the middle is the front carbon. What do I have? I've got H coming straight down. Okay? Now, is it coming exactly straight down? No, it's actually coming towards you a little bit. Okay, because look, is it coming straight down? No. We have an H going like this. And we have an H coming up like this. That's the front carbon. Okay? We're looking this way. Now let's do the back. The back carbon is right behind the front one. You're not supposed to be able to see it. Right? Can you see the back one? No, the front one's blocking it. Okay? The way we do this is, it's almost like the entire circle is the front carbon. We can't see behind there. Okay, like a disc is here. But we can see this H back here coming up above that. We draw that like this. Okay? Coming from the top of the circle there. We can't see back there how it's connected to that carbon, but we just know it's back there. Because the back carbon's right behind the front carbon. Looking at the back, one straight up, one to the right and a little bit down, one to the left and a little bit down. And that is supposed to be this drawn on the board. This is called a Newman projection. Okay? Why do we do this? Because it's much easier to see certain things this way. It's a convenience. That's why it was created. Because before people were like, I just can't tell from this. And then someone's like, well, if we draw it like this, we can tell things better. And that guy's name was Newman. He worked at Ohio State. He was a chemist. Okay? I actually knew someone who worked with him. All right? Said Newman was always talking about melting point. Hey, did you get what was your melting point? All right? It was back in like the 70s and 80s. Newman was old then, and I'm pretty sure he's passed. Okay. Getting close. I reckon at this point I just wanted to do that because really what you need to be doing is getting into the Newman confirmations. We also going to have, and we'll pass back to quizzes, is the cyclohexane chair confirmations. Okay? It's on the flip side of the purple. Okay? Two different types of confirmations is going to be a big thing here, okay? please spend some time reading and working problems on that over the late break. Questions? What's the cyclohexane? Yes. You watched the nomenclature video? Okay, if you want to pick your quiz up here, would someone close that here?